Hey folks, I'm Michael, and I love making things sound better, and today we're going to be walking through a sound system design. This is a show that I mixed 3 years ago, and we're going to be looking at the brief, the gear list, and how exactly I took all the specific challenges and settings of that show to make a design with the PA. It's a little bit unorthodox though, because we're going to have to hang the PA 12 feet in front of the stage, and we're going to intentionally break some of JBL's recommendations for deploying the VRX array. So stick around for that. We're going to answer a few more questions like what's different about deploying a constant curvature array versus a traditional line array? How can we predict horizontal coverage when our prediction software only gives us vertical coverage? And is gain shading a useful tool when deploying an array? Before we jump in, make sure and grab my Audio Mass Survival spreadsheet. That can be found in my audio toolkit with a bunch of other super useful stuff. You can get that at producedbymkc.com/audio toolkit. It's got over 30 different calculations you can use when putting together your designs or in the field to help you make decisions faster and better for better sounding sound systems. So let's take a look at the brief, walk through the gear list, then we'll jump into the design step by step. Let's go. All right, this show is a dinner for a local nonprofit, and it's going to be held at the Fayetteville Town Center, a local event space. I was freelancing for a VOD3 event production out of Lowell, Arkansas, and I needed to make sure that speech was crystal clear throughout the entire audience. There wasn't a musical or performing act, maybe a couple of video rolls, but bottom line, the biggest thing is to make sure whoever's at that podium can be heard throughout. So I'm not super concerned about getting a fancy subarray in there. I need to make sure that I have really great coverage front to back and left to right, and it feels even and natural throughout. So for venue data, it was super nice to have this Google SketchUp drawing. From it, I can pull any of the measurements I needed, and that was super handy. So from that, I was able to determine that the beams in the ceiling are 18 feet. So that's a pretty low total trim, but we'll see how we can deal with that a little bit later. The audience is seated at rounds, and I'll get the specific dimensions of that coverage area, but this tells me where the tables are going to be, therefore where I need to point my speakers to cover the audience. The stage is 24 feet wide by 12 feet deep and 4 feet high. It's going to have that drape line folding around it. And I knew that the tables, so therefore the audience, were going to start 10 feet in front of the stage. The front of house mix position is at the very back of the room, so I know that I'm not going to be actually mixing from prime PA coverage because I really want to focus my PA coverage on the audience. I needed to be mindful of sight lines to the screen, so I couldn't have speakers hanging super low or any off fills that might get in the way of these tables near the sides looking at the screens. Okay, here are some more audio specifics and the gear list. I knew I was going to have a flown PA off of a 40-foot stick of truss that I was sharing with the LD, and they were going to have their stage wash on there too. So it's going to have two 1-ton motors on the very end. I could have put my PA anywhere across it as long as the lights could get around it. I knew from that the max I could actually get the top box of my array was probably going to be about 16.5 feet, because if I got a 12 by 12 truss that's hanging, that's a foot, and then I knew we were going to have motors sunk up into the truss with truss picks, so that saved us a little bit, but saying another 6 inches to maybe another foot, I would lose of trim just from getting the truss up in the air. So 16.5 feet of top box trim is best case scenario, and it was probably going to be a single point hang because I'm not that great at span sets for doing a front and back to really get a specific tilt of the angle, and I wasn't going to have separate motors to really bring the front or back up and down. I knew that I could place front fills on the edge of the stage, but nothing on sticks off to the side again because of sight lines. My specific gear list was 8 JBL VRX 932 LAPs, and I'll have 2 fly bars, so that's the 2 flown arrays. All the rigging and span sets and stuff were included. These are self-powered boxes, so I needed to run power up there. I don't have to use all of them in the air. I have 8, so I could do a hang of 4, a hang of 4, but later we're going to determine that I go with 4, 3, or 2 in the air. And I need to make sure and choose this box specifically in the prediction software because the weights are different than the passive version of these boxes. I had 8 QEC CP8s for front fills, fold back if I needed them. And my console was a minus M32 and had a DL32 stage box that was going to sit behind the stage. I did not have an external DSP, so any speaker processing needed to come from the console. and I had two QSC KW181 subs. Low end is not a high priority for this show since it's not a concert, so it's probably going to have to bow down to aesthetics and logistics to get those subs out of the way, because I can't fly them and they need to be out of the way for any traffic in front of the stage. All right, so let's jump into the design now that we have all of our venue data and speaker data. On the front end of my designs, I like to fill in any missing gaps in data and start to firm up some of those variables, because we could put our speakers theoretically anywhere, but our target coverage area, the speakers we have, and the given specifics of a show, it's going to determine what's going to happen. So let's get some of that ironed out, then we can plug that data into our prediction software. So the coverage area of this particular audience is 96 feet wide by 70 feet deep. So that'll go right into our software. Just from looking at this, I know that not a single speaker is going to be wide enough to cover this entire audience. So I'm going to subdivide and conquer. So my left array is going to cover this half, and the right array is going to cover this half. It is this beam right here that I'm going to be hanging my PA off of. Well, it's going to have a 40-foot stick of truss, so that determines my maximum width of the two arrays between each other. And I know that it is also 12 feet down stage. And so that is going to determine the x-axis, or the point in the room in which the PA is hung off of. And we already talked about I have a maximum trim height of 18 feet. I have truss there, and so it's going to be under it. So best case scenario is 16.5 feet. So by knowing where that beam is, my coverage area, my total trim height determines the X, Y, and Z placement of my array. And I do know that I can put front fills on the front of the stage, so they're going to take custody of the first 10 feet in, and that can go a maximum of 20 beyond that. So then that just determines where my front fills are going to hand off to my mains. You need to also remember that I don't have to use all 4 of the VRX I could put in the hang. I have 8 total, so I could do 4 and 4, but we're going to determine the total vertical coverage needed and see if maybe I could take off that bottom box and then use it as my front fills. And I like having matching products in the mains versus the front fills for a better tonal uniformity. And that way I can also use them within the same system design software, because QSC products, which are the CP8, I have to use Ease Focus 3. For JBL, I have to use VRX LAC, so they don't talk to one another. As far as subwoofer placement, aesthetics is going to win on this show, and it's not a concert, so I'm not super concerned about having a fancy sub array. So they're probably going to go here, left and right of the stage. There's a lot of symmetry in this design. There's a left and right screen. The stage design has symmetry, so they're probably going to get symmetry out of my sub placement. Okay, so that firms up our placement of the PA. We still have to figure out aim and coverage and stuff, but let's take a little bit closer look at the actual speakers we have in their particular coverage areas. So in my MKC audio toolkit, if we scroll down, which you'll get this with my Audio Master Survival spreadsheet, is my speaker database. So these are speakers I use all the time and just wanted to have a common set of data to work with. And these are the specs I need to look at. So here's the VRX 932 LAP. And I can look at all these properties here. It tells me a lot about it. It is a constant curvature array, meaning I don't have variable splay angles in the array. I'm stuck at 15 degrees. And it has a horizontal coverage of 100 degrees. And we'll use that later to determine, hey, is this flown PA actually going to be wide enough to cover what I'm asking it to do? So what's left, now that we know this data of like where is the hang going, how wide is it, is how many of them do we need? What's the vertical aim of the array? So at what down tilt is it going to be? The horizontal aim. So do I need to tow the PA out a little bit? Do we need to tow it in? And what's the overall per box gain shading if I'm going to use gain shading? And then on the back of the VRX, there's a +3 or -3 HF lift starting at 1K. And so I can maybe ask my top box to have a little bit more top end to throw, since it's probably going to have to throw a lot farther than the bottom box. And the other data for the QSC CP8 is I know it's also self-powered. It is just a single trap point source box. It is 90 degrees by 90 degrees. And so it is conical in shape. So if I use it for a front fill, those are the coverage angles I can expect out of it. All right, now that we've plugged in some gaps and we know a little bit more about a PA placement and the specific coverage angles, let's jump into our prediction software and start making some design decisions. All right, first up is mains vertical aiming. So how many boxes do we need, and where are we gonna, what kind of tilt are we gonna get out of the array to make sure we have even front to back coverage? So here I am in VRX LAC. We can't get a 3D look or even a top-down 2D look to determine horizontal, so this is only going to help us with vertical coverage. We'll get the horizontal later. So for setting up the file, just in case you're unfamiliar with this software, we have up to 2 arrays we can look at. I have our flown array right here and a front fill, and you can turn them on and off right here. We have the specific boxes that we've chosen. So I've chosen the 932 LAP. We can choose the specific gain shading per box right here, and I can turn up the HF +3 or reduce it -3 with each of these little dots. The room dimensions I can determine here in the actual PA placement. I have the top of the flown PA right here at 16.5 feet and as 12 feet into the room. And I have the front fill on the downstage edge, 4.5 feet in the air. And these planes right here determine the start and stop of my audience, and they really just assist with aiming. I have right here is my front fill coverage start, the 10 feet to 20 feet. So I've drawn a separate plane for that. And then I have 20 feet back to 80 feet is how deep it is from where the front fills and the PA hands off. So I like being able to subdivide that so I can isolate that coverage. And then I have a little line right here that's at the exact audience mid-depth. So if I need to do any aiming or decisions based off that, that's a quick visual reference for me. Lastly, I can look at this frequency response graph down here and see how I'm doing from the top and front to back. That's my biggest concern here. Okay, let's measure the vertical coverage needed since I already have my PA placed. I can pull up Pixelstick, and I have this guy right here at the top box, and I can drag it here. And to the very back is a -10 degrees. Now if I put this guy at the bottom box and I have to have it throw here to 20, is -45. So there's a 35-degree coverage needed from front to back. So I do know that the VRX, it is 15 degrees per box. And so 1 box isn't enough. 2 box is 30 degrees, so that's not enough. I need 35. So it looks like 3 box gets me to 45 degrees. So that's enough to cover this entire audience. So I can do 4, but that'll give me 60 degrees and also put my bottom box really low. So therefore reduce or increasing my front to back distance ratio. So I don't want to do that. So I'm going to go with 3 boxes. So now that we've determined the number of boxes, we can measure our front to back distance ratio. So when you fire up the program, it starts with the plane definition as coordinates. So you're going to put in on this graph the actual coordinates of the plane. But if you go here to distance and angle, I can put my rangefinder, which is this little crosshair, at a specific point. And so it's glitching out right now, but I'm going to re-put in these coordinates. And I have this rangefinder at the top corner of that array. And I can look, and it tells me from the front point of plane 1, which is right here, and then the back point or the rear point of plane 1 is right here. So I can compare these 2 numbers. So I'm looking at the top box to the back row, and that's telling me that 69.2 feet, and I can remember that. And then if I move my rangefinder to the bottom of the array, which is about 11 feet, then 13.5 feet, and if I have that and I measure to the front point of plane 1, which is right here, that's 13.5. So I have a 70 feet from the top box to the back row, and I have 13.5 from the bottom box to the front row. So that's going to give me my distance ratio. And I can go over here to row 100 on my Audio Math Survival spreadsheet. And if I put in 70 feet or 69 from the A box or the top one, and then 13.5 to the bottom, that is a 5.1 to 1 range ratio. So that's throwing 5 times as far, which is telling me that is a 14 dB difference if both boxes are equal volume. So that's a lot to overcome there. That also measured to the middle just for fun, and that was about a 7.2 dB difference. So we have our total vertical coverage needed, and our range ratio. So 5:1 is pretty significant, especially with the constant curvature array. But now let's see how we can fix that. So my definition of success is a less than 6 dB variance from 1K to 10K front to back in the top end. And why I'm not too worried about the low end is that's usually up to the array geometry or how long the array is. So if I look at 200 Hertz right here and go to SPL mapping, we can see that on the main array, it's just kind of blobbing out. So you have to have a long line array to be able to steer low frequencies, and doing some EQ on the bottom box doesn't help because those aren't isolated because they're all just moving out omnidirectional, or mostly omnidirectional anyway. And so just looking at this frequency response right away from the very front row and this row right here, there is this bump in the low mids, but I know I can't do anything about it, so I'm not looking to shape that with how the angle I'm getting out of the array. So I'm mainly concerned about steering where the waveguides have sole custodian of the array, and that's usually about 1K on up, or 1K to 10K. So I need to make sure there is a less than 6 dB variance and tonal uniformity front to back. So I don't want just at a single frequency for it to be okay at less than 6 dB, maybe 4K. I want it to have a pretty flat response from 1K to 10K. And this is the biggest beef and why we're going to break some of JBL's manufacturer specifications, is that in their manual, they rely heavily on gain shading to make sure you have it even at 4K. So they really hammer home on that single frequency instead of looking more at the total frequency response of the array. And they say, hey, yeah, we've got all the front to back of the audience squeezed into a less than 3 dB variance at 4K front to back. But they really don't do a good job of highlighting, like, okay, you have to look at the full frequency response. What can you control with the HF +3 or -3 shading, the total number of boxes used. And so I think they just try to highlight that one feature of like, hey, you have individual volume control over the boxes, but there actually gets some problems is if you have severe differences in gain shading throughout your array. And that's covered really well in a video that Nathan Lively did, and I'll link to it below, but he's actually taking a look at one of my designs that I did a few years ago and used gain shading on a care array. But anyway, check that out and you can see how the low mids get kind of wonky when you start to gain shade, and we'll jump into that there. My approach is get right number of boxes by determining the vertical coverage needed, and now we're gonna play with the total array tilt and then see if we can also marry up some of the HF gain shading and make that work. And yes, that is still technically gain shading. It's more along the lines of EQ, of just lifting that. We are adjusting the total gain of the high frequencies, but why it's okay to do that is that they have isolation from each other in those boxes. Since we can really fine tune 1K, it's only going at this specific direction. We're not getting it wide and spread out like 200. That means those boxes do have individual isolation. So I know when it's just throwing there within that particular top box coverage, I can trust that that high end is going to be only there and not get weird stuff when it's summing together with the other boxes. So I think that's a great tool to use on this particular array. We also have to keep in mind our front fill. We need to make sure that this very front row has adequate level. And we can see here, if it's at unity, along with the rest of the array at unity, it is very high. So right now it's at 118 dB up here at 4K, and the bottom is at 104, so the very back row. So that is a 14 dB difference, which is a no-go. So we need to make sure that we solve that by bringing down from 1K to 10K that spread. First, we're going to make sure our front fills and our mains are aligned. We already know the crossover point is 20 feet in, so we can measure either with Pixelstick or our rangefinder to get the delta in the delays here. So if I go over here to my arrow tool and measure the distance from that bottom box to 20, we already know that's 13.5, and from 0 here to 20 is 20. I can put those values into my spreadsheet and get some useful data. So here I've converted those distance offsets to milliseconds, and you can do that by going to the top and going to wavelength and putting in those in feet, and it'll spit out the period or the time it takes to complete that wave. And that tells me just from those two things, the front fills and the mains having a difference in time, this tells me the time offset to align them at that specific point and how the front fills are going to be 3.14 dB less loud than that bottom box throwing to that point. So I'm going to probably need to shade it down because I don't want the people at 10 feet to even get blasted, and I want a smooth alignment from an amplitude standpoint at that 20-foot mark. Okay, so we're going to enter that delay value into the mains since it's getting to that 20-foot deep into the audience mark first. And we're going to put in 5.7 to 5.75 milliseconds. And so we can see here that the low end is matching up much more nicely and summing together because they're now arriving together at the same time at that point. Okay, so let's actually get rid of our front fill for a little bit and look at our frequency response. And this definitely proves, again, that we really need it because this is sitting under the array at 10 foot in, and look how far down our high-end frequency response. It's huge. So we definitely need that front fill. We'll come back to fine-tuning its level. But first, let's fine-tune the display angle of the top array. So I do know that the top box is going to have to throw farther, and it's going to need some more help in the top end to do that. So let's give it a plus 3 dB lift. And I can see here on these traces, I'm already getting a little bit of a lift, but now let's aim it down farther and see if we could steer some of that towards the back. So we're actually shooting this top box a little bit past the first row, because we're really tied to the array configuration of being able to have a single point hang and it have a single point through exactly one of these holes. So I'm tied to putting it in 2 or 3. So I know that 7 degrees down puts it in 2, and this is the response I get. I'm going to ignore the red probe for now because I know that the front fills are going to do that, and I'm pretty happy with this. I have a 105.4 dB at 4K and then 109. So that's right now about 3.5 dB difference between front and back, which is great. And I have pretty even tonal uniformity of from 1K on up. I'm not having any crossing of the two, like the mid depth now goes above an HF than the back. So I want them to all maintain fairly flat response and not cross each other. So that's definitely good there. So just to experiment, I would be forced to move it to the third, and I'm there. So if I put it down at 15, that is a much more severe difference between the high end and the front to back. So at the front, it's 114, and the rear 102. So that's a 12 dB difference. So that right away tells me that I'm going to go with the second position, which was at -7 degree down tilt. And now let's bring in the front fill. And now I want to, throughout the real front of the audience to the back, get less than 6 dB. So let me bring it up. And now see that this front fill is at 118 and the back is at 106. So that's 12 dB. So I've brought this front fill down to -8 dB. And so I'm looking for a smooth transition from the front to this other point at 20 foot in. So we break my rule a little bit, and that the response from here at the crossover point to the front, they merge here. They don't quite cross, but what I can look at is that the front response here from 1K and up is flat. This has a little bit of a down tilt, but I can know that these are even here. And so I can know at this front row of my main coverage, my front row in quotes, and then my front row of the full coverage are even here in the top end, and that's a win for me. So I can look at the very top at 4K is 111.7, and my bottom is 105.6. And so that is just over a 5 dB difference. So I am really happy with that. And so I have done +3 on my top box, left my middle at 0, and my bottom box on my flown array is -3. And then for my front fill, I've left it at 0 and shaded it down -8 dB. So that's where I'm going to end up for the vertical coverage on this design. So now let's move to horizontal coverage. Okay, for horizontal coverage, we're going to aim through the middle of the middle. So if I know that my truss or my PA is going to be hung on the truss right here, they're going to be at the ends here about 40 feet out, and I need to cover right here. So if I'm at the end right here and I need to go through the middle of the middle. So I'm going here and here, and I'm at the end of the truss and going to need to aim right here through that. So that tells me I'm going to have, looks like a 5-degree out angle. It's going to be hard to be super exact in the field. I probably won't have a ton of time to get out all of my protractor and all that to make that happen. But that tells me, hey, I'm going to need maybe a 3 to 5 degree out tilt. So we don't have a way to predict that with VRX LAC, but being able to use this quick way to look at it in SketchUp really helps. So I know I'm going to have an out tilt, but is a 100-degree box enough to do that? So I'm aiming through the middle of the middle. But now let's go back to spreadsheet. I'm going up here to speaker coverage to FAR and LAR. So forward aspect ratio talks about if we were to draw a rectangle that would encompass the kind of fan-shaped coverage of a speaker, what would be the length and width to get a ratio for that speaker coverage. And lateral aspect ratio means if a speaker is throwing a certain amount of distance, what would be the coverage across a flat surface if we're hitting that. So if a speaker is throwing 10 feet and we have a LAR of 1.53, that means the width of it would be 15.3. So that would be our multiplier there. So with a 100-degree speaker, which is what we have in the air, that is our multiplier. So I can look at that and see, okay, what is the actual throw distance of our bottom box? That's 13.5. And then our top box is 70. So I can use that lateral aspect ratio multiplier to get there. So if we go back to SketchUp, I know my PA is off of this truss, and I know it's starting coverage 20 feet in, which I happen to know is about this table. Now we can look at how wide we need to make that happen. And if we're throwing 13.5 times our lateral aspect ratio multiplier of 1.53, it gives me about 20 feet. I know that if our bottom box is throwing 13.5 feet, it's going to be able to spread out enough to cover 20 feet wide. So I can give us a little tool right here by knowing that if I draw this line here across here, that's 20 feet. I'm going to click and drag it. We're starting here. I know I'm only covering about that wide at that short of a throw, but at the back, I know I'm going to be able to do more. So let me grab him and put it at the back, and that's 70 feet. So that's 3.5 of 20 feet. So if I make some more friends here and drag him out, so that's 1, 2, 3. Let's add a half and a half. That's overlapping there. And then I'm going to click and drag these. So this is more or less the trapezoid of coverage of a 100-degree box only being able to throw 13 feet, the 100-degree box being able to throw 70 feet, and how it's going to be able to spread out. So now I know that my front fills need to really be focused on taking care of these people right here and these people. And then I can mirror this on the other side of this array. So the spots that are going to need the most help are the stuff that is near the array and is not covered. So that's basically right here, and right here. So when I'm tuning the system and really fine tuning the display of it, I'm going to really be paying attention to these spots and make sure it's covered. But I do know that a 100-degree box is going to be able to cover it. And another way I can prove this is by going back here and converting the coverage area of the audience to our forward aspect ratio. So it's 70 feet deep and it is 96 feet wide, but we're going to subdivide coverage. So I'm going to divide that in half. That means I need a FAR of 1.46 to make that happen. And I can convert FAR to speaker coverage. And that says I need at least an 86-degree speaker at mid depth to make that happen. Going a little bit wider is good because I know my my bottom box throwing to the front is throwing at even less of a distance, has less time to spread out, so it's not going to cover as much. So having a 100-degree speaker, both from looking at this calculative standpoint and measuring it out on throw distances right here, gives us our answer that yes, our VRX are going to be able to cover horizontally. And now we're going to jump into Map 3D. And I've recreated this array with a 110 degree speaker and kind of guesstimated on the vertical point to simulate what our VRX are doing. And I've put another 110 degree wide speaker here on the stage, and we can look at the coverage. So if we look top down, I need these speakers to be out at a 30 degree splay to get it pretty even throughout here. So if I single this out, that's where it's doing. I want to be able to hand off at half and cover to right here. So this is a good estimate at a time of knowing that, yes, I'm gonna have to take my front fills, tilt them out a little bit so they can own their own respective coverage areas. All right, that wraps up our design. Here are the 3 big takeaways I got from designing this show. Trim height really matters. Every extra inch really helps, because having this severe 5-to-1 distance ratio of a 70-foot throw to the back and only 13.5 to the front just makes it harder to get the high end really tailored to be even from front to back. So lean on your front fills when you need to, because looking at VRX LAC, if I did not have these on the show with my PA being so far out into the audience, it makes it really, really hard to get it even front to back as well. And thirdly, definitely start and learn from your manuals and your manufacturer specifications, but I just happen to disagree here with how heavily JBL thinks you should rely on gain shading to get to the needed coverage response. There's just a difference in design philosophy. Those are obviously super smart people there, not trying to dog on them, but my approach is to observe or to preserve tonal uniformity in the low mids first before I start to rely on gain shading to get the needed high-end response out of an array. Really appreciate you sticking around with me and hope this was helpful for you. Every time I do one of these, I learn something, and so I hope you're able to walk away and apply this to your designs. Make sure and get my Audio Math Survival spreadsheet at the link below, or producebyMKC.com/audio toolkit. That was how to deploy a VRX array and a really low trim height. I'm Michael Curtis and love making things sound better. Thanks for watching. See you in the next one.